This is Lab 1, Constant Velocity. This lab was conducted to demonstrate the predictability of the position of an object moving at constant velocity by comparing an observed model's position with a simulated model's position. For the observed model, a video of the basketball rolling on a table was inputted into Tracker to analyze the position at each frame. For the simulated model, the code was adjusted in GlowScript using the corresponding time increments and details from the observed model. All the data was paired using Google Sheets to create a graph. The predictability is accounted for in Newton's first law, which states that an object will stay in constant state of either motion or rest until acted on by an outside force. During the experiment, it was found that an object with constant velocity will move in the same direction, speed, and time as a model that is simulated. Here we can see that the simulated and observed paths were found to be similar in their trajectories. The condensed data is shown on the left for each corresponding model, with the red being simulated and the light blue being the observed. This is the basketball on the surface along with the graph from Tracker. It can be seen that the ball is moving in the negative x direction or to the left. Using some of the data values from the right, calculations can be made. And here we were able to see that the observed start time is 0 and the final time were 0.8. And these values can be directly pulled from this graph or from this data table. And you can see that the starting time is 0 here, but the end time is not on this slide. The initial position of the ball can also be taken from here, which is 0.007 in the x direction, and then should be 0 and 0 in the y and z direction. The initial velocity can be calculated by taking the change in position over the change in time, which yields an initial velocity of negative 0.882 in the x direction and 0 in the y and z directions. And each time interval was approximately 0.0165 seconds. The system in this experiment is the ball, and the earth and the table are considered the surroundings. The ball initially begins at 0.007 meters and is rolling with a constant velocity of negative 0.882 meters per second. The sign indicates the direction of the movement. If the axis directions had been swapped, the sign of the position and velocity would become positive. Since the surface is smooth, friction is minimal and air resistance can be mostly ignored. Therefore, the ball will continue rolling at negative 0.882 meters per second until acted upon by an external force, which is Newton's first law, and it will not accelerate, which is Newton's second law. Regarding the coding section, the basic details of the balls are inputted using the calculated data from a few slides ago, with the initial position as 0.007 in the x direction and the initial velocity as negative 0.88 in the x direction. And the time step is set to be 0.016555 as in delta t, and the initial time is going to start at 0. Since the ball is in constant motion, the acceleration is 0. And according to Newton's second law, when the acceleration is 0, the force must also be 0, which can be seen on line 54 where the net force vector is adjusted to be the 0 vector. This loop runs the code at an increment of 0.0165 seconds until a total of 0.8 seconds are reached. Here, the model can be seen in a little larger diagram, and the fundamental physics principles involved include Newton's first law, which says an object will stay in motion until acted upon by an external force, and Newton's second law, which says that the force of an object is a product of its mass and acceleration, which in this case is 0. In order to identify errors, the system and surroundings must be identified. The system is the basketball, and the surroundings include the table and the earth. The deviation from the simulated data can be due to the negligence of air resistance or friction. And lastly, an object moving in a certain velocity will not change until interacted by an external force. Therefore, the position in the space can be modeled as the final x equals the initial x plus the velocity in the initial x directions times the change in time. When comparing both sets of data, they are nearly identical. The net force is 0 as the forces acting on the ball are the gravitational force and the normal force, which cancel out to become 0. And as air resistance and friction are considered negligible, it can be said that the net force in the x direction is 0. Overall, regardless of the object, the path of the motion can be simulated as long as the net force is 0. And that concludes my presentation. Thank you.